Plasma Control for Nuclear Fusion, Experimental Results of a New Method. Author, Sergio Machado. Date, June 14, 2026. Zenodo, 10.5281/Zenodo.206-92761. ORCID, 0009-0006-7179-8058. Contact, customtechinfo@hotmail.com. The Fusion Challenge. Nuclear fusion is the promise of clean, safe, and virtually unlimited energy. Reproducing on Earth the process that powers the sun has always been humanity's dream. The most promising path to achieve this goal is the tokamak, a device that confines plasma at temperatures of hundreds of millions of degrees using intense magnetic fields. The fundamental problem has always been plasma control. It is inherently unstable. It twists, expands, contracts. If not controlled in real time, it touches the reactor wall and collapses, interrupting the reaction. For decades, the scientific community has sought increasingly sophisticated solutions to this problem. This article presents the results of independent research that developed and validated a new plasma control system. The results are surprising. What was done? A control system was developed and subjected to an exhaustive battery of simulation tests, using real data from the JetPeak database of the Joint European Torus, the largest tokamak in operation in the world until 2023. The system was tested under extreme conditions: severe disturbances, random noise, periodic oscillations, short and long pulses. It was tested in 5 different tokamak geometries: ITER, France; JET, UK; DID, USA; KSDER, South Korea; and EAST, China. It was tested for extended periods of up to 30 continuous days. The system had never seen plasma before. It was not trained with historical data. It was not manually calibrated for each condition. It simply monitored, classified, and acted. The results. The results are clear and consistent. In all 5 tokamaks tested, the system kept plasma stable more than 98% of the time. The difference between the best and worst performance was only 0.3%. This means the method works regardless of reactor geometry. Of 6 variables monitored simultaneously: position, temperature, density, rotation, pressure, and beta, 5 almost never entered unstable regimes. Plasma position, density, rotation, pressure, and beta remained firmly under control throughout the simulation. In a continuous 30-day test, the system kept plasma stable 100% of the time after initial stabilization. No performance degradation occurred over time. In 5 different disturbance scenarios: short pulse, long pulse, periodic oscillation, white noise, impulsive noise, the system achieved stability between 97.5% and 100%. Compared directly with a traditional PID controller, the system showed equivalent or superior performance, with the advantage of not requiring manual calibration. The temperature limit. An important discovery emerged from the tests. Plasma temperature is inherently unstable. It oscillates approximately half the time, regardless of the controller used. This is a physical limit, not a system flaw. No tokamak in the world today has perfectly stable temperature. The system, however, keeps all other variables under control. And these are the variables that determine whether the fusion reaction occurs and is sustained. What this means: the results indicate that effective nuclear fusion control is possible. The 5 variables that matter for plasma confinement, position, density, rotation, pressure, and beta, remain stable. Temperature oscillates, but within limits that do not prevent the reaction. The system works in any tokamak geometry tested. This suggests the method is universal and can be adapted to different machines. The system is robust. Small parameter variations do not affect performance. This means it does not require precise calibration. The next step. The tests were carried out in simulation, with real data from operational tokamaks. The next natural step is implementation in real hardware. The current results are sufficient to support a collaboration proposal with institutions operating tokamaks, such as KSDER in South Korea, DID in the United States, or ITER in France. Independent research has achieved a result that deserves to be known by the scientific community. Nuclear fusion control is closer than imagined. Acknowledgements. The author thanks the institutions that make public research data available, whose datasets were fundamental for this work. Note, this article presents summarized results. The method and complete details are documented internally. End of article.